seen that K values are very important parameters as we use the K-means. So what we attempt to do now is to scale further because in the last class, so I'm supposed to share this. In the last class, that was a stage 6 or class 6. We actually saw that the K-means algorithms depend on pre-chosen values for K. So you need to choose a priori that is beforehand. You need to choose a value for K. But the stuff we want to look at now, we want to see that it is not actually needed sometimes when we use this model to have a pre-selected values of K. We could actually undo it in a different way, and that will help us still have a better clustering. And one of them is what you call hierarchical clustering. So in hierarchical clustering, the root word is hierarchy. Hierarchy means from the lowest to the topmost, from the bottom to the top. So hierarchy, from the followers, the list of the followers to the boss at the top. So the objectives we are trying to cover in this class will be to understand agglomerative. Don't worry about that. You'll get to know it before you finish the class. So agglomerative simply means bottom up. That means you are going from down up. Okay, like a process that is going, someone is growing gradually from the down level to the upper level. So that is, we want to understand agglomerative clustering. Then the next thing will be for us to learn how to read dendrograms. So there is a shape called dendrograms. We're going to learn how to read such diagrams. Then, of course, we use these two powerful libraries, the SciPy and the Scikit-learn, for creating or plotting hierarchical, for modeling hierarchical clustering. Then finally, we're going to compare linkage methods. We have different linkage methods. So you'll get to know what linkage methods are. So let's have a setup. And our setup will be needing this library, NumPy, Matplotlib, SciPy. So in SciPy, that's where we're going to get the cluster hierarchy, where we're going to now import the dendrogram, linkage, then F cluster. Also, we're going to use Scikit-learn, and Scikit-learn as a library. We'll take cluster as a module, and there we'll be taking agglomerative clustering class in Scikit-learn cluster. Then from Scikit-learn datasets, we'll import Matplotlib. Okay, so those are the setup we'll be using for this class. So the first part is to do something we call the family tree analogy. So that's trying to explain agglomerative approach, agglomerative clustering. How do we explain it? Now think about it. As level 1, we start. So every point is its own cluster, every point. So when everybody's starting, it's like you have 5 people in your family, or let's say you have 10 people in your family. So each person is standing alone. So every point is its own cluster. Then the next level is you find two closest clusters. So you find 2 family members each. So they will come together. So 10 will reduce to 5. There were 10 before when each person was holding a cluster. But now after 2 closest people have joined, so our total number will become 5. Is that okay?
Yeah.
Okay. Then eventually we can now merge them all into one cluster. So when you find those 2 closest clusters, you merge them into one cluster. So the 10 clusters we started with are reduced to 5. Now you would repeat, this is the word, you repeat until only one cluster remains. So you keep repeating until at the end of the day, we now have just one cluster remaining. The output of that kind of exercise will be a tree. And that tree is known as dendrogram. So it will be showing us all the merges. That means all the merges, all those clusters, how they merge over time. So that's what we're going to get from the dendrogram. And the key advantage here is you don't need to know K beforehand, just like I said earlier on. So you could just work without any prior knowledge of your K value, and you'll still be able to generate a great model. So let's see something here. This is just an example with 5 data points. So I used the 10 data point before. So imagine you have 5 data points. So the next thing is you will cluster those ones that are like that, those that are close to each other. You cluster them, this also, and this, you cluster them, so that the value will reduce. The number of points will reduce to 3. This will be 1. This one will merge, making 2. This one will merge, making 3. Then you repeat the procedure. You look for those ones that are close again. You merge them until you have just one cluster. So the next thing I want to create, let's create dendrograms. Dendrograms. That's the next attempt. Now, in creating dendrograms, there are some certain things you need to take note of. You need to know about the linkage. So you know about linkage methods. For these linkage methods, we have the one called single method. We have the one called complete method. We have another one called average method. Then we have another one called word method. Can you list them for me?
Okay, so single, the methods are single, complex, average, and word.
Okay, thank you. So those are the linkage methods we do have. So you have minimum distance between members. That is the single. Single method is described as the minimum distance between members. Then there is the complete method. So complete method is the opposite of single. That is the maximum distance between members. Then the average, of course, it will average all the distances. Then there is the word. This word minimizes variance increase. Word linkage is usually used in hierarchical clustering. So let's try and do some plottings. Here we compare, I want to compare linkage method. So we pass in the make blobs function, and we give it this argument, or this number of samples is 50, centers is 3, and on and on and on. So the methods, this is what we're interested in. This is what we're interested in properly. We want to check the effect of each of the method here. And we do that by plotting. So let's see what we generated. When we use single linkage, this is the output for complete linkage, this is the output for average linkage, and this is the output for word linkage. So like we said earlier on, complete linkage gives us a better overview. So as you can also see from the diagram, look at these dendrograms. Look at the clustering of the shape in orange.
Yeah.
You can see the wiggling nature of it, the wiggling nature of this one. But if you look at the complete method, can you see there is a sense of balance and orderliness? So it's well said. Well said. Okay, so that's the complete linkage. you see kind of symmetry, I mean, proper kind of joining up of the clusters. Then look at the average. You also notice that the average has somehow skewed and erratic. You see the way the shape, how they look like. You see this one also. They are not at the same level. And finally, we have the word linkage. Word linkage. You see how that looks. And for word linkage, you just use to minimize variances or variance between distances. So that's the idea of a dendrogram. But how do we plot it? Very simple to plot. We just use a tool, the library, and we'll be able to do some plotting. Okay?
Okay.
So let's do some plotting now. Okay, let's okay. So can you tell me the 4 types of linkages we have?
The 4 types is complete linkage, average linkage, word, and simple linkage.
Okay, tell me something about each of the books.
Simple linkage is just as the name says. It's simple. The complete linkage is very well formed. The word is a little bit deformed, and
okay, use description to explain.
And the average linkage is going to give you a simple average of the distances.
Okay, then the single.
The single,
okay,
is going to give you the minimal distance of the linkage.
Oh, between members, okay?
Yeah.
The complete linkage.
The complete linkage is going to show you everything, the max distance between the linkages.
Okay. Then the word would tell you what? It minimizes.
The word will just show you the smallest version, minimize variance.
Variance. Okay, so it minimizes variance increase. So it's stop or it's clip or increment in variances. Okay, so can you see now what do we call this shape?
Which shape?
These 4 shapes where we use linkages. What do we call them? All these shapes. What's the technical name?
Samples?
No, it's called dendrograms. Say it.
Okay.
Can you say it? Dendrograms.
Yeah.
Say it. I said you should say it.
Dendrograms.
Again?
Dendrograms.
Okay, so these are the dendrograms. We're forming some shape using these types of linkages. So in practice, we usually use a word linkage. You can also use complete linkage. So it depends on what you're working on, but word linkage often works best for compact spherical clusters. Actually, one of the reasons we use a hierarchical clustering is because k-means is very constrained when it is exposed to spherical data. So data that are sphere, it seems like circular. So k-means struggles with those kind of data. So we use hierarchical clustering in such situations. And here we use word linkage. It is very, very suitable for spherical clusters, and it's best for compact clusters as well. So let's do something now. We want to do what we know as agglomerative clustering. So in agglomerative clustering, we move from bottom to the top, bottom to top. So let me run this code. So here we use agglomerative clustering here. and we pass in just two parameters, the number of clusters, and as well the type of linkage. And we make a label by predicting and fitting X. So we go ahead and make a plot. So I don't need to waste time on describing the plot again now. So we make a plot and we're able to generate these clusters. So 3 clusters here. Then if you practice it also, you could also generate such, find some clusters. Okay, so last, I briefly talk about this. So it's a brief discussion actually. So, but what I encourage you to do is to try and see how you can draw this. That's how you can plot these dendrograms. So just come to this line of code. I already sent the previous codes to you. So please, you need to practice them. You need to work on them. That's how you'll be able to get to use them properly. So you can see here, we're drawing dendrogram. And to draw a dendrogram, we pass in the links, we pass in the arcs, we pass in the number of labels as true, and that is what produces. So this is the code. This is a major line of code that produces the shape dendrogram. Then of course we have set up the X, the number of samples, and all those other input variables that we would need for the plot. So try your hand on this, just 16 lines of code or thereabouts, less than 16 lines of code actually. So I wanted to, okay, I explained this already. Okay, I wanted to summarize that agglomerative, or what we call bottom up, is used to merge up clusters. And I told you what that means. So you look at how many data points are you starting with? Maybe you are starting with 10, for instance.
Yeah.
That's just an instance. So you look at the closest one, you merge them to form a cluster, and you repeat the process until you reduce everything to a single cluster. Can you see this is reduced to just a single cluster? At the end of the day, this is already, at the end of the day, you see this blue line is a final cluster. So you see this yellow or the orange are clustered, then they're joined. Then eventually we have this single, we have them reduced to just a single cluster with a blue line. So the blue line form the final single cluster, the final single cluster. So we have the internal clusterings, but we're caring for the outward one, the single clustering line that eventually results. Okay. I also talked about the dendrograms, so I'll show you now. So with dendrogram, you visualize the tree where all the merges happen, how they happen. Then one key thing you must take out of this place is when you are using agglomerative clustering, you don't need to specify K. You can cut your dendrogram anywhere. Then we talked about the linkages, the linkage methods, the average, the complete, the single, and the word. And we said word usually works well. So when to use, when to explore, so we use a word, when to explore different numbers of clusters. We need a visual representation of cluster hierarchy. Then we're working with smaller data sets. Actually, it's not as efficient as K-means, but it's also a good thing. So take note of that. So we use it as we use hierarchical clustering when we want to explore different numbers of clusters. We want to visualize a cluster hierarchy. Hierarchy means from lower to higher. So in this, if we take complete linkage, for instance, the hierarchy, we have, for this side, we have the lowest ones down below. Then we have another, so you can take this 1, 2, 3, and see how they are joining, how they are forming, until we have the final topmost line joining them. So when you want to visualize the hierarchy of your clusters, you will use a hierarchical clustering. Equally, when you want to see you want to work on smaller data sets, you could use hierarchical clustering too, though not as efficient as k-means, but you could use it without specifying k value beforehand. So the next stage now will be to look at DBSCAN. DBSCAN. So by DBSCAN, D means density, B means base, that's density based, spatial clustering of applications with noise. So that's very important. So we are dealing with spatial clustering of applications with noise, density-based spatial clustering of applications with noise. What do we mean by application with noise? But before then, let me show us what we're going to cover here. So we're going to understand why k-means fails on non-spherical clusters. I said earlier on that k-means is restricted and it fails, it struggles. Okay, I said it struggles when we use it on spherical data or clusters. And that is why one of the reasons we use DBSCAN instead. So why do we have that? They want to look at the concept, the key concept, the core concept of DBSCAN, the Epsilon, the minimum samples, the core, the border, the noise point. They will attempt to apply DBSCAN to complex shaped data and undo outliers, or in another way, we call it noise. Again, we set it up by using these main libraries, NumPy, Matplotlib, Scikit-learn. For Scikit-learn.cluster, I'll be importing k-means and DBSCAN. So there are classes in cluster module. Scikit-learn.datasets, we import make moons, make blobs, and of course, we'll do some pre-processing. That will be using standard scaler to ensure that the dimensions, the values we use are both vertical and horizontal, assuming 2D, assuming they're 2D, so vertical and horizontal, the values we use are scaled the same way. So we'll not have a situation where our data will fit to one point or lean towards one side. Okay, now let's run this code. Now, can you see this shape?
Yeah.
So the first shape, so let's see what we have from our code. We are making moons, x underscore moons, then y underscore moons. How do we make it? We use a function make moons. So with make moons, we set up the number of samples, 200, the noise level, 0.5%. Oh, sorry, 5%, I mean. Then the random state of 42. So the first thing is we use k-means, we want k-means to try. So because what we want to show here is why is it that k-means fail when we're dealing with spherical shape? And of course, you know that moon is a sphere. Moon is not a line. It's a spherical shaped object. So that's why we're making moons. We use x moons and y moons as our variables that we store with make moons function. Then after we have done that, we tried km, an object instantiated on k-means, and we'll give it this just two basic parameters. And after that, we fit and predict kmx moons. And based on that, we come up with some plotting. And this plotting gave us this shape. So we have the moon-shaped data. Now let's see. We notice here that k-means can't undo non-spherical shapes. See the results. that this guy has. So he struggles to make struggles to find the right clusters. So that's clustering problem is shown here. You can see struggles that you have 1, you have 2, but you can see that it's actually deviating from the real shape of the moon. So the result is a state of failure. So it tries to find round clusters, not knowing that moons are curved, not just what they are curved shape. That's spherical. Okay, so chemists struggle, it suffers to make a clear-cut clustering with spherical shape. So the next thing is want to look at the DBSCAN again. So we've talked about DBSCAN. So DBSCAN shines in this place because instead of looking for round groups, what DBSCAN looks for is the crowds. So what do you mean by the crowds? Where are people packed together? And those one will form clusters. Then it also can be that even though you have an open field with an assembly of people packing together, you will notice that sometimes there will be someone that will be far away somewhere that will not be close to other people. We call those ones outliers or noise. They just show up intermittently, but they are not really part of what we're trying to study. So those are outliers, the noise. So we watch out for that. The key concept here is the epsilon. Epsilon, it means neighborhood radius. So how do we describe this? How close must you be to count as a neighbor? So if I say somebody is my neighbor, how close would the person be to my house before I say, oh, this is my neighbor? This is my neighbor. So the parameter that handles that in DBSCAN is called the epsilon. Okay. The next one is the minimum samples, MinSamples. So the description is the minimum neighbors to be called. How many friends do you need to be popular? So that's something like that. That's the minimum sample. So I want to be popular. How many friends do I need to be popular? That is what minimum samples handle. Then we have the core points. So the core points handles popular kid with a lot of friends, somehow related to that. Or we say it has greater than or equal to minimum samples, neighbors within EPS. So core points relate both EPS and minimum sample or minimum point. Then there is the border point. So the border point is near a core point, but not enough neighbors. Imagine if guy that is very popular, his friend, though is closer to a popular guy, a popular kid. Some people will know him, but he will not be as well known as his friend that is popular. So he's a friend of a popular kid. So that's the border point. Then the noise point. Noise point, this one, they stay alone. They don't have any friends nearby. So these are the terms to be using, and those are the main concepts for DBSCAN. Can you read them out for me, the key concepts?
Key concepts. Term, oops. Neighboring radius. How close must you be to count as a neighbor? MinSamples. Minimum neighbors to be core. How many friends do you need to be popular? Core point has greater than MinSamples neighbors within EPS. Popular kid with lots of friends. Border point near core point, but it's not enough neighbors. Friends of a popular kid. Noise point. Neither core nor border. Loner with no friends nearby.
Thank you. So after now, when we're done in the class, we'll soon round off so you can, I don't want to load you with material. So you're going to do for me is that you're going to take note of each one of these and read them up and have a better feel of them. Okay, so let's see this code that is used to make something. Now, we are trying to explain each of these parameters with this code. So we want to explore the core, border, noise point. What we just talked about here. What you just talked about on the epsilon, the minimum sample, the core point, the border point, the noise point. Okay, so look at this. Can you see we have this data point 1, 2, 3, 4, 5, 6. Now we're trying to explore this. So we say 5 neighbors within EPS. So these are 5 neighbors. Can you see those 5 neighbors? Those are inside. The blue line is the EPS radius. You will notice that the other green is rotating, it's not inside, right?
Yeah.
Okay, so it's so we have the EPS radius. So here we have the core. The core here is we have 5 neighbors within EPS. So we talked about core points as greater than or equal to minimum samples within EPS. Okay, then as you can see, we have border. This one is near core, but it's less than the minimum samples neighbor. So you can see this yellow is at the border point. It's close by, but it's not within the EPS. Is that okay?
Yeah, it's okay.
Then can you see this one, this cross? Sorry, I said cross. This is a X, okay, or this cancellation symbol. You see it's far away. Even though we knew that the yellow was not within the EPS, but it was still very close, isn't it?
Yeah.
But look at this star, or this X rather, is far away. The point of this X is 5 by 5. So it's far. Where we have, and most of these ones range between 2 to 2. So it's far from them. So we say this is noise. So if this guy has accident, he might likely die. You understand? Because no one is near him. This guy, if he had accident, he can still survive because you have some coral. You have 5 neighbors. You have some neighbors around and close by. Do you understand?
Okay.
Okay. So the point is that this green one too, even though it's a core point as well, but it's not really within. We're talking about within now. Okay. So this X is also known as the noise point or the outlier. Now, can you hear that? How it's an outlier. That means something that is lying outside. Liar as lying. Not to speak word that is not written now, but to lay down. It's outside, it's lying down outside. So we call it an outlier. Is that okay?
Okay.
So we've seen the EPS radius, the core point, the border point, the noise point. So let's go through this again. The EPS is the neighborhood radius. How close must you be to be counted as a neighbor? The minimum samples is the minimum neighbors to be called. How many friends do you need to be popular? How many friends do you need to be popular? Then the core point. So for the core point, we're looking at it as greater than or equals to minimum samples neighbors within EPS. So it's like having a popular kid with a lot of friends. Then the border point. This border point near a core point, but not enough neighbors. Friend of a popular kid near a core point. So this guy is near a core point. This core point. This core point. So this guy is near this core point, but it's not within. So we call it border point. Then the noise point far away entirely. Okay. Now let's check DBSCAN and see the action of DBSCAN. Okay, so what we're trying to do here is we saw the other time that the k-means failed in some clustering, but where k-means fail, DBSCAN usually succeed. Now look at, can you look at this shape now? We're trying to do cluster. We want to cluster these purple colors, I think, purple and the yellow. So if you look at the k-means, you will notice that it couldn't do a good job. So you see, it did not cluster these. This cluster belong to this cluster. So they are supposed to be together, isn't it? They have the same shape, okay? This guy and this guy, they're supposed to be together. They are not clustered together, even though they have the same feature space that are related. So k-means could not do that clustering. But DBSCAN was able to do that. So it was able to group together all the shapes, all the colors that are purple, and was able to group together into another shape, into another cluster, all the shapes that are yellow. So this is what we say when we commented that DBSCAN is able to deal with applications that has noise, whereas k-means failed to do that. So the shape is not usual shape. So DBSCAN was able to do the clustering. Again, you remember DBSCAN is density based. So when there is dense shape or density of info, density of noise, so it's able to make a separation and able to do a proper clustering. So we're doing spatial clustering of applications with noise. So you look at the output or the image this clustering for. You see this looks much more clustered than this. So these two are supposed to be together. These two are supposed to be together. So k-means could not undo such a scenario. So we use DBSCAN instead. Okay. Do you have any question, or does it make sense? Hello?
Sorry. Yeah, it makes sense.
Okay. So what we were able to do here is that DBSCAN was able to separate these two moons, these two shapes of moons, separated them, clustered them. But k-means struggled. It broke them apart. So DBSCAN separated them. So DBSCAN successfully separated the two moons. It found two clusters. Then the noise point was 0. But k-means struggled to do that. Now let's talk about some of the parameters. The parameters of DBSCAN: density-based spatial clustering. Okay, so here we have a different clustering here. Let's see some observations about them. Effect of EPS parameter. We've talked about what EPS is. So we want to see the effect when you use different EPS parameter, Epsilon, when you use different value, what do you end up having? Now, as you can see, for the first shape, so again, let me refer you back to something. So I want to carry you through as we use them. Remember, EPS neighborhood radius. How close must you be to be counted as a neighbor? How close must you be to be counted as a neighbor? EPS radius. How close must you be to be counted as a neighbor? So to be counted as a neighbor, how close must you be? So it is the EPS value that helps us to achieve that. Now, from this code, I set up a system of different EPS values of 0.1 through 1.0. And we add a model, DBSCAN model, implemented in it with EPS equals to EPS, meaning that it will iterate through each of these epsilon values and create a model from it. So minimum samples, we're using 5, and we have filtering predicting using the XMONs that had been created before. So this is the core of the application, of the implementation. This is a core. This is a core. All other ones are just aesthetic and drawings. So this is where the training happens. Taking EPS from each of this value, then we're taking the minimum samples. So for AX, EPS is zip. We're calling on the zip function because we're using args and using epsilon together. So we need to use zip here. And we're flattening the axis, and we're taking the EPS values. So we set up the model DB, we fit it, and save it in this container labels, and fit and predict on it, taking the argument of XMONs. So after we did that, so all these are just the setup for the drawing. Okay. So the first thing is here, when EPS was 0.1, EPS was 0.1, we have 19 clusters. 19 clusters. This is a cluster for example. This is another cluster. So we have different clusters all around. So at the end of the day, we have 19 clusters and we have 22 noise. Can you see now? Now, when the EPS value was 0.2, how many clusters do we have?
2 clusters and 0 noise.
Thank you. So we have 2 clusters. 2 clusters. We have, this is the second cluster. And 0 noise. So you could see there's no noise anywhere. That means there's no outlier, no noise points. Okay. When the EPS was 0.3, again, we had how many clusters? How many clusters? EPS of 0.3.
2 clusters.
2 clusters, 0 noise. Thank you. The same result as in 0.3. So 0.2 and 0.3 gave us the same result. 2 clusters, 0 noise. Now, it's getting much more interesting here. Here we have EPS of 0.5. When our epsilon was 0.5, we ended up having 1 cluster, 0 noise. 1 cluster, 0 noise. When EPS value was 0.7, we also had 1 cluster, 0 noise. When EPS value was 1.0, we had 1 cluster, 0 noise. So what do you think? Which of the parameters gave us an as it is now from what we have, give us a good value, give us good shape that we can actually rejoice over? Which of them?
EPS of 0.2 and EPS of 0.3.
Thank you. That's cool. So EPS of 0.2 and 0.3 did a good job in helping us to achieve a clear clustering, and also we had no noise. So there was clear separation of the modes to the two shapes. So the two clusters they belong to. When we use EPS of 0.5, 0.7, 1.0, even though there was no noise in each instance, yet the clustering was not a full true representation of what we had. So what do we mean by this? So let's make some observation. And this observation has been printed out here. When EPS was too small, you have too much noise and the clusters fragmented. That means they were broken apart, they were broken into pieces. That was when we use 0.1. The EPS value of 0.1 gave us 19 clusters. That's fragmentation. So everybody wanted to be the boss. So everybody was having his own cabal, forming his own group, because the EPS value was too small. Then at the other side, when the EPS value was too large, so we see the clusters just merged together. So there was no clear separation. Then we had a soft spot when the EPS value was 0.2 or 0.3. So for this case, we are considering it was just a right value. Now, take note, this does not mean that every time we want to use DBSCAN, we must use epsilon of 0.2 or 0.3. It doesn't state that. It's just showing to that in this case, we are considering. For this instance, we are exploring the just right EPS value for this, where the EPS of 0.2 and 0.3. So that's one parameter that is very important that we have looked at. So what we are trying to do is to understand parameters. Okay, let's move on and check something else. So we want to check the effect of minimum samples. Minimum samples is another parameter. So what will it do? Minimum samples here. Minimum samples, the minimum neighbors to be called. Minimum neighbors here. So you could see here, we have 5 here. Why not 3? Why not 2? Why not 1? Why not 10? So let's see the effect of that. So that's the next exploration we want to go into. So effect of minimum samples on parameter. Now see these results. When we use a minimum samples of 2, so we have 0 noise points. Minimum samples of 5, we have 0 noise points. Now, when we use minimum samples of 10, we have 3 noise points. And when we use minimum samples of 20, we have 200 noise points. Now, what do you mean by noise points here? If you watch properly, or if my projection is showing clearly, you will see this at the noise point we are talking about. No, that yellow is not part of it. Let me take out the yellow shade. That's not part of it. When you look at this, these are the noise points. You see them, they are, I'm trying to look for the word now. There is, okay. There's a word I want to use, but that would be signal related. There's something called population. You see that they are defaced. So almost everything here is being defaced. So they are being truncated and being terribly marred. Okay, so that's why we have noise point of 200 there. So you could see again that minimum samples has great effect on what the noise point turned out to be. And you also notice that when we have the value between 2 to 5, we came up with 0 noise points, showing to us that when we go to higher minimum samples, that will lead to a kind of noise that is outrageous. So it will lead to when you are trying to strictly define your core points, they will be generating more noise. So you place save around acceptable values based on the situation you are addressing. Okay. The next thing I'm going to bring up here is how to create. So we have talked about two major parameters, the epsilon, then the number of the minimum samples. So you've seen the effect on the outcome in relation to the noise and also in relation to the number of clusters that were formed. So let's see DBSCAN with outliers. So this part 5 will be where we're going to call it a day. And we're going to do some summarization. So I'm going to send you the script so you could work on them. Now, the DBSCAN with outliers. Let's run this code and see how we do. Okay. So here you have our DBSCAN detected 21 noise points, and we added 20 outliers. So look at something, the original data with outliers. So all these are the data point, the blue ones, the red star are the outliers. I've explained what an outlier is. Look at k-means. So the outliers affect the centroids for the k-means. But what happened with DBSCAN? So DBSCAN outliers detected as noise. So it was able to detect the outliers. And you see that it pointed them out. It pointed out all the outliers that we added. We added the outliers from our original data. So we want to see how these two models, the DBSCAN and k-means, how they will do, how they will behave under the effect of outliers. So DBSCAN was able to detect the outliers and mark them out. So coming up with a very good clustering. So this shows to us that DBSCAN detected the noise point by detecting those outliers as noise point. So DBSCAN works to detect outliers. So that's a great advantage of DBSCAN as well. That means where k-means struggle to detect outliers, DBSCAN conveniently detect it. So you're going to do part 6 as a practice exercise, and you're going to complete your code, and let's have your solution. So what are the advantages? So we have DBSCAN advantages. So you see it finds clusters of any shape. That's very advantageous. Unlike k-means that is limited strictly by, that is limited when it faces shapes that are spherical, like moon shape. Another thing is you don't need to specify number of clusters. It handles that by itself. Unlike k-means where you need to, by a priori, set up a value for your x, for your k. Then it identifies outliers and noise automatically, just like we did now. Those outliers we added to the data, it saw them as outliers and pointed them out. However, we have disadvantages. Of course, there must be trade-off. It depends on what you're looking for. So we did have the disadvantages of DBSCAN. One of them is no need, you need to tune your IPS and minimum samples. You have seen that when you don't use the right epsilon or you don't use the right minimum samples, you tend to have fragmented clusters. You also tend to have excessive noise generation in your model. Then another thing is you're going to struggle with varying density clusters. It doesn't work well when you have high definition. So it works mostly, it works better where you have noise. And that's where the name comes from. You can see the name. The name says density-based spatial clustering of applications with noise. So it works with uncleanliness. It doesn't work very well where things are clean. That's just a simple word here. So it performs very well when you expose it to clean, with unclean data where you have a lot of noise outliers. Or at the other side, it struggles. So you need to tune the helps. It doesn't work well in very high dimensions also. Then when do you use them? Or when do you use DBSCAN? You use DBSCAN when you are dealing with non-spherical clusters like moons, circles, non-spherical, anything that is then you use it for data with outliers. Then you also use it when you don't know your K beforehand. So these three are very important. Non-spherical clusters, data with outliers, when you don't know your K beforehand. So the next stage will be comparison of algorithms, which one I'm going to do now. So, and those algorithms will be comparing the K means the hierarchical clustering and the DBSCAN clustering. So we'll be comparing them head to head and we'll see how they do. I think we can finish it up. Let's finish it up now. Let's finish up this.
Okay.
Okay, so we've already seen them, so I'm not going to dwell more on them. So but let me quickly review the objectives of this class and see. So we understand why K-means fails. You saw this, right? K-means height failed on non-spherical clusters, okay? So it's struggle to cluster moon-shaped object. Then we've learned that DBSCAN's core concept are the Epsilon, the minimum samples, the core. So I've seen this one. Then we have applied DBSCAN to complex shaped data. You saw that, right?
Yes.
Yeah. And we saw that it handles outliers and noise very well, more than K-means. So let's quickly run through this last one. Again, I'm not going to take time, just maybe 10 minutes. I should be done with this one. So here, comparing clustering algorithms. So the question will be, or our objectives will be, we want to compare K-means, hierarchical clustering, and DBSCAN. So we want to understand their strength, the weakness of each one of them. Then we'll learn how to choose the right algorithm. We've already talked about when to use them. So we build a decision framework. I'm not going to, so let me just run this place. Okay. The algorithm at a glance. So algorithm, we have the K-means, the type is a centroid based, hierarchical connectivity based, DBSCAN density based. You see centroid, the center K-means connectivity, where you have to see how those lines connect and join. That's hierarchical, sorry. Then the density based, the shapes that are complex. Do they need K? K means it needs K. Hierarchical is optional. It's not compulsory. DBSCAN does not need K. Then the shapes, how do they handle shapes? K means handles spherical shape only. Hierarchical is better than K means. And DBSCAN handles any shape. Handles noise. The first two, K means and hierarchical, they don't handle noise. DBSCAN handles noise. Let's create this. So here we have round blobs, we have moons. So here we have concentric, we have elongated clusters. So we want to see how they will do. And we could even predict before we run that and see how they will do. So I want to compare the 4 algorithms. So here we have the original data. So look at K-means. Let me switch to my pen. my pointer. So you see K-means here did a bad job. So the cluster was not complete. So it has separated this cluster and this cluster. That's K-means. See hierarchical. Hierarchical also did a bad job. It separated this from this. Even though it did well with the yellow shape, but it separated the purple shape. But see DBSCAN. DBSCAN found the two clusters, even though it gave us just a little outlier, just one single outlier. But DBSCAN is better in separating the shape here. So you see that when we deal with moon-like shape, DBSCAN is a king. Is that okay?
Yeah.
Okay. Then the next one will be concentric shape. So let's see concentric shapes. Okay. So when you look at the concentric shapes, look at here. We have the original data. This is the original data. See the K-means. K-means was not able to complete this concentricity. The concentricity was not okay. Okay, this concentricity. See this as well. See this as well. Then the DBSCAN found 10 clusters here. Okay. Then let's look at the elongated shapes. Let me treat them together, then we'll make the comment. So the elongated shapes or elongated clusters. So this is the original data. Then K-means made three clusters. Hierarchical 1, 2, 3 clusters. DBSCAN found just one cluster. So let's compare them and see how they did perform actually. So what we found is that for round blobs, K-means did fine. Hierarchical did fine. DBSCAN did good. So great for round blobs, but DBSCAN was just good. When we handled moon-like shape, K-means failed, hierarchical failed, and DBSCAN did great. When we undo circles, K-means failed, hierarchical failed. That's a concentric. Then the DBSCAN did great. When we did elongated, K-means failed, hierarchical failed, DBSCAN did good. So the key point is this: K-means best for round, well-separated clusters. Hierarchical is similar to K-means, but gives you a dendrogram. Then DBSCAN, best for weird shapes and when you don't know K. Is that okay?
Okay.
Yeah. So what will be your decision? Decision will be you follow this framework. So you start by thinking, do you know how many clusters you want? If you know, if your answer is yes, then you ask yourself, are they round shape? If your answer is yes, you go for K-means. Otherwise, you go for DBSCAN. That is, do you know how many clusters you want? If your answer is yes. So you ask yourself again, are they round shapes? If your answer is yes, go for K-means. If your answer is no, go for DBSCAN. Now let's go back. Do you know how many clusters you want? If your answer is no, you ask yourself, is there noise? Is there any outlier? If your answer is yes, go for DBSCAN. If your answer is no, if there are no noise, there are no outliers, then go for hierarchical. Does that make sense?
Yes.
Can you summarize that? Can you repeat it for me?
So practically asks you if you
said?
want to know the amount of clusters. It asks you to know the amount of clusters you want. Yes or no. The yes part takes you to a question to ask if there are if they are came, then for the no side, it asks it asks you if there are noise. If there is noise, you should go with BBSCAN, and then if it's no, you should go with hierarchical.
Hierarchical. Okay, thank you. So that's the decision framework for deciding which of the model or which of the algorithm should you go for. So the next thing I want to show here is a reference table. I call this quick reference table. So feature, you have the k-means, you have hierarchical, you have the DBSCAN. So for feature, specify k. K means yes, it's required. You need to know k. For k means hierarchical, it is optional. DBSCAN, no, it finds it by itself. Cluster shapes is good for spherical only. Hierarchical, mostly spherical. DBSCAN, any shape. Then undoes outliers. So k means cannot undo outliers. It affects its centroids. Hierarchical, it cannot undo outliers. DBSCAN, it undoes outliers elegantly. It marks them out. Speed. The speed of k-means is very fast. I'm not going to talk about the O log for you. It's a bit, just forget it's the O loggers. Just know that k-means is fast, hierarchical is slow, DBSCAN is medium. Then parameters. So for k-means, we have the number of clusters. That's the most important parameters. For hierarchical, we have the number of clusters and the linkage, where we have the single linkage, the complete linkage, the word linkage, and the average linkage. Then for DBSCAN, you have the epsilon and the minimum shapes. So you've seen that epsilon, when you don't tune it very well, that's when you don't choose the right value, it can generate unnecessary noise and also fragment your clusters. The minimum samples also, you need to be sure of the right value you are using. Then now about the visualization. For k-means, is scatter plus centers. For hierarchical, you can create a dendrogram. Then for DBSCAN, you can create a noise and scatter plot. Now, it's best for what? K-means is best for large data sets and known value of k. Hierarchical is good for small data sets and that need hierarchy. DBSCAN is unknown k and weird shapes. So you can do this practice exercise and come up with your answer to this question. So let's do a summary. Choose k means when you know k. Can you read it with me? Choose k means.
Choose k means when
you know k.
Clusters around, data set is large, speed matters.
Speed matters. Choose hierarchical when you want
hierarchical when
different k values. You need a visual hierarchy dendrogram.
You want to explore data set is small, medium.
Then you choose DBSCAN when you don't know k.
Choose DBSCAN when you don't know k. Clusters have weird shapes. That has outliers noise.
Thank you. So let's go back to the objectives and see. So compare k-means, hierarchical, and DBSCAN. Have we been able to do this?
Yes.
Okay. Understand the strength and weakness of each one. Do we know where to use which?
Yes.
Okay. Learn to choose the right algorithm. Have we learned to do that?
Yeah, we have.
Okay, so of course, when you know the strength and the weakness, so if you know that, oh, this guy is weak here, so you know I should not choose it when it's area of weakness. So when you know it's strong here, so you know, when you know strength and weakness of a model, it will make you know what and when to choose. Okay, then build a decision framework. You should, have we done that? Decision
yes.
framework. Yeah, so we did talk about decision framework. Do you know how many clusters you want? If it's yes, are they round? If it's yes, choose k-means. Do you know how many clusters you want? Yes. Are they round? No, choose DBSCAN. Do you know how many clusters you want? No, Is there noise or outliers? Yes, choose DBSCAN. Do you know how many clusters you want? No. Is there a noise or outliers? No, choose hierarchical. So far, so good. Thank God we've been able to cover those today. And next time, by the grace of God, we move to feature scaling. Up until then, have a nice time. Please do go through your code, please. This is very important. Type it out yourself. That will help to strengthen your neurons and master those concepts very well. I'm going to share the video as usual. And if there is any question, reach out. Thank you. God bless you.
Thank you.
Okay.